Okay, guys, it's about 7:30 in the morning. Decided I'd put up a video, and it's kind of the beauty of this online presentation. I get to put videos up when it's convenient, and you get to watch them when it's convenient. So if you're a night person, I guess you may want to watch these at 2:30 or 3 o'clock in the morning. If you're a morning person, pick your poison. The content in this video, I think, is far too low for a graduate level course. But from the perspective of your professor and me, I don't want to build a house on sand, and I don't want to take anything for granted. One thing I learned from teaching previous graduate level courses is we're going to use t-tests and t-intervals in a much more complicated, from a much more complicated perspective, if you will, later on in the class. So I don't think it's going to be about a 50-minute video, and I don't think it's going to waste anyone's time. So please watch it, even if you know how to do a t-test. I'm going to incorporate a little bit of R in here and show you some things that we can do. So guys, again, the focus here is to just review t-test and t-intervals. We begin with a claim about a population mean mu, and the criterion here is that the population standard deviation is not known, and we're going to use information from a sample to test the claim. So I want to illustrate this process in in great detail. Okay, so let's say, for example, that excuse me, that there's a national average, or I'm sorry, a national test, and the average on the test is 74. And we want to see how our students at our school district compare to the national average. Well, it would be reasonable to go out and collect a sample, and in this case I've collected a sample of 10 students, and I hope there's 10 scores there. Yeah, there are. So we have the 10 scores that are given. So before I'd like to, before we get into the problem, let's, officially set up what we want to test here. So the null hypothesis would be that the mean, the average for this district students is 74, and I'm going to construct what's called a two-tail test here. That the mean is not equal to 74. The two-tail test gives us some flexibility that a directional test doesn't. I'm going to illustrate a directional test here in a few minutes anyway. So the next thing we would want to do is set up our alpha value. And guys, this is just, as we'll learn in the next video, this is just the probability of committing a type 1 error. So we're going to allow ourselves a 5% chance of a type 1 error. Again, that'll be explained more in the next video when I get into type 1, type 2 errors and power calculation. Okay, so what I'd like to do now is I'd like to get out of the screencasting and go to R, and you can see what I've done here is I've already type the numbers into R. So, and this is a convenient way. We're going to have data presented in this class 3 different ways. First of all, when we have a small data set like we have here, it's pretty convenient to use what I call the C function, and that just allows us to enter our data directly. We're also going to use Excel files where we convert to CSV. I illustrated that in a previous video, and there are actually built-in data sets in R that we're also going to use. So lots of different things are going to be going on. Well, guys, first thing I'd want to do is just, I know the sample size because it's such a small data set. But nevertheless, I want to illustrate this because our data sets may not always be this small and manageable. Now, the next thing I'd want to do is I'd want to get the mean. So the mean is 70.8, and I'd like to take a look at the standard deviation. So I'm going to write this down on the blackboard, and so when we go back over there I'll have that. So the sample for this group is 70.8, and the standard deviation, I'm going to go out a few places, 6.161 should do pretty well. Okay. Now I'd like to take a look at some pictures. So let's just run a histogram and make sure we haven't got any severe skewness, and that passes the eyeball test. Severely skewed would be if either the first or the last bar was a lot higher than the other bars. So we like to have symmetric data when we run a t-test. So that's cool. And I'd like to look at a box plot to see if there are any unusually high or unusually low scores. And it turns out that this score down here, it looks like it's lining up to 55, is an outlier, in relationship to the other scores in the data set. Now, again, I've got a small data set here, so I can visualize just take a look at the scores and see that it has to be 55. But let's say I had 200 scores, and it wouldn't be as easy to pick out what the lowest number is. Well, I can always use sort function to put my data from low to high. So I know from the box plot that the lowest number has to be the outlier. So I've got an outlier of 55. Not exactly what I'd like to have, but hey, life isn't perfect, right? We have to deal with the data that I guess we got to play the hand that we're given. Okay, so let's scoot back over here to the air server, so you can see that I've written down the information from our sample. Now, the next thing that kicks in is the theory, and this is what I call the sampling distribution. Kind of hard to write on this thing, so cut me a little bit of slack, guys. Okay, I can't write anyway, so when you challenge me, it's even a little more difficult. So sampling distribution tells us this: that if we could dive into our population and pull out samples 10 at a time. Now, what's so incredibly special about 10? Well, that's the size of our sample size. So more in general, if we pull out n at a time, in this case is 10, so it's going to be easier to talk through that way, we would get a first sample mean. Now, is that the one that we got? Probably not. But if we could replicate that, a couple seconds later, we would get a second sample mean. And once we get those calculated, dive back into our population and pull out 10 more measurements, add up the scores, we get our third sample mean. And if you can imagine doing this forever, it'll be a long homework assignment, right? And we don't have to. We think about this theoretically. If we could do that forever, and again, just in case there's some confusion here, let me back up a little bit. We have our possible sample means from a population. And again, if we went in and drew out 10 scores, we could easily find the mean of the first 10 scores that we get. 2.7 seconds later, we could pull 10 other scores out, get its sample mean. And guys, it should make sense to you that if we did this forever and ever and ever and ever, that we would exhaust all possible sample means of size 10. Well, we call this the distribution of sample means. And if you think about it, let's think about the one that we got. What was it, 70.8? Now, which one is this? Well, we have no idea. But we know that if we were able to get all of the sample means, that theoretically we could put all those numbers into a calculator or some means of technology. and we could create a histogram. And if the histogram looks guys, when they were giving out artistic abilities, your statistics professor got none. But it turns out we could do a histogram, and we could smooth out the histogram. And theory tells us when we have the distribution of sample means, size n equal 10, with sigma unknown, that this distribution will follow what we call the t-distribution, with degrees of freedom. Well, I'm not able to write down here for some reason. I'll tell you what, let me get back up on that line. For some reason down there is not allowing me to write. So degrees of freedom n minus 1. So guys, clearly the distribution that we're drawing our samples from, our sample has degrees of freedom equal to 9. So this mean that we have of 70.8, where is it? Well, we have no idea. We know it's in here someplace. Maybe that's it. Maybe that's it. Maybe we just don't know. But what it allows us to do, knowing the distribution of all sample means, how all sample means will behave, where they're centered, what's the variation look like, we can determine the likelihood of getting a sample higher or lower than a particular value. So we know that our problem, our t-test, is guided by the t-distribution, degrees of freedom equal to 9. Now, the first thing we want to do is we want to find our standardized measure we want to standardize our sample. And we do that with what's called a t-score. And the t-score just tells us how far away from the claim that our sample mean is in terms of standard errors. So our calculation is going to be made by 70.4 or 70.2? Okay, 70.8. And I think this is 6 point, I should have written it down, 161. That's easy to remember. Because I don't know why, but down when I get down at the bottom, it doesn't want to let me write. Okay, so let's grab a calculator, whatever it may be. We could do this in R if we needed to, but I think it's going to be just as easy to put this in our calculator. And when I get this, I get negative 1.64. So this tells us that our sample of 70.8 is 1.64 standard errors below the claim in H sub O. Now, the next thing we do is we examine more closely the distribution of sample means. And at the end of the day, the logic is we say to the national test score 74, we're going to just give it to you. We're going to say that the mean of the distribution that we're drawing from has mean of 74, which if you think about it, that would be a t-score of 0 in the middle of our distribution. And we're going to come in, we're going to define two lines that at the end of the day represent sample means that are too far away from the claim for us to believe the claim. Now, guys, ultimately what we're doing here is we're trying to see if there's statistically significant difference in the national average and the average of the 10 students at our school district. Well, what we do here is we come in, this line in the sand, if you will, is defined by our alpha value. So as I said earlier, we're running a two-tailed test because our alternative hypothesis is, well, I can't draw, not equal to up there. I'm not losing my mind. I just, for some reason, I'm not, there's parts of my iPad that aren't accepting, well, that's really strange. Huh. Well, pretenders are not equal to there. Yeah, finally showed up. Okay, so our alternative hypothesis has not equal to, which means that we're going to divide our rejection region into two equal parts in each tail. Well, again, I'll give you an illustration of a directional test here in just a second. Now, what we need to do is we need to be able to come in and find the line in the sand, if you will, that separates what we call here would be the fail to reject region with this region that we call the reject region. So if we get a mean down in here, that's too far away from the claim of 74 for essentially for us to believe the claim of 74. However, if we get a claim, or I'm sorry, a sample mean somewhere close to the claim as compared to one that's a long way away from the claim in terms of standard errors, then there's no reason to take that small difference and conclude that we're significantly different than the 74. So the alpha value we talked about earlier, which is 0.05, so each of these would be obviously 0.025, just really defines our rejection region and how far away from the claim is too far for us ultimately to buy into the claim. Well, we need to get some points here, okay? Where do these lines in the sand actually occur? So let's clean up our drawing a little bit. And it turns out we can go to R and find that out. Now, if you think about it, if we had 0.025 right here, and we have 0.025 here, so we have combined 5%, then we have 0.95 between the two, so the kind of the inner segment. So let's go over to R, and I'm going to show you how to find the lines in the sand here. Okay, R has a kind of a cool function called PT and QT. So PT and QT are functions for T distributions. PT finds probabilities, and QT finds scores from our distribution. Well, with a a certain amount of percentage of the area under the curve to the left or to the right, and I'll show you how that works in just a second. So what we want to do is we want to find the score from the distribution that has 2.5% of the scores below it with degrees of freedom 9. So notice in QT you're asked to put in two things. The first thing you're asked to put in is the percent below, and the next thing you put in is the degrees of freedom. Now, we should know that the other is just going to be the positive of that, so the other line in the sand, the one to the right, defining the line in the sand for the right tail. But let's just go ahead and verify that the right tail, or the right line in the sand, as I usually call it, has 0.975 below it, and you'll see that gives you the same thing. So if we go back to our drawing, I should have written this down. So let's just call it 2.62. I think it'll be close enough. And negative 2.62. Now guys, our t was negative what? 1.64? Yeah. So with this being 0, our t would fall about right there someplace. So our decision would be to fail to reject H sub O. Now, another method. And the one we're going to use as we get into more sophisticated measures is called the p-value approach. So what we do here, instead of defining the lines in the sand, what we do is we appreciate that we're drawing our samples from the t-distribution, again, degrees of freedom 9. And what we do is we look at the standardized score for our sample. I don't know why I keep having a hard time remembering that. And we look at the area to the left of this. Now, because we're constructing a two-tail test, we have to appreciate that the likelihood of getting something above 1.64 is equally likely to getting something below negative 1.64. So we have to find the combined area in both tails, again, because we are conducting a two-tail test not equal to in our alternative hypothesis. You know, it's hard to say. Our alternative. That's hard to say for a Kentuckian, and maybe not for you Northerners. I don't know. So what we need to do is we need to find the area in those tails, and it turns out with R, it turns out it's very easy to do. So area in the tail, we're going to use the PT function. So PT. And what we want to do, PT, we put in the value that we want to find the area below. So I think we were negative 1.64 degrees of freedom 9. And that gives us an area of 0.0677. Now, we could have multiplied that by 2, or if we're just kind of, as an illustration here, if I want the area in the upper tail, what I would have to do is take 1 minus PT 1.64 degrees of freedom 9 to get the same value. Now let me illustrate why I have to take 1 away from that, just so there's no misunderstanding. So again, my answer is ultimately going to be this times 2. Let me go ahead and so 0.1354 approximately. Now, why would that area in the upper part be entered as 1 minus? Well, guys, remember what you get with the PT function in R is you get whatever value you put in. You get the area below that. But since I want the area above that and the area under the curve is 1 square unit, or 100% of our information, I have to take the entire value, subtract out what I get as the value below, and that should make a lot of sense that gives you the area and the tail that we actually want. Alright gang, nevertheless what we end up with is we end up with our p-value being equal to 0.1354, and our p-value is greater than or equal to our alpha, which gives us our same decision of failing to reject the null hypothesis. Now, in cases where our p-value is less than alpha, then we would reject the null. Okay? Now, if you think about it, why does this work? Well, if we have alpha equal 0.05, that's saying that in our distribution of sample means, we're going to put half of our rejection region, 2.5%, or 0.025, in the left region, or I'm sorry, in the left tail, and 0.025, 2.5% in the right tail, because this is our rejection region. If we get a sample mean that results in a t-score, a standardized score here, and we take its corresponding part up here, which is positive, and guys, we would do the same. If we had ended up with a positive, we would also look at the negative. We'd look at both tails. When is this total area going to be below 0.05? Well, it's going to be below 0.05 when we get a standardized test, a standardized score from our mean, which is left of the line in the sand. If we get something over here, this area is going to be bigger than 0.025. Multiplied by 2 is going to be bigger than, I'm sorry, this area here is going to be bigger than 0.025. When multiplied by 2, it's going to be bigger than 0.05, which tells us that we're in this area, which is our fail to reject area. Okay, so guys, what we've got here is we've got a t-value of negative 1.64. We end up with a p-value equal to 0.1354. And we end up with a fail to reject our null. Now, the next thing I want to illustrate to you is how we do a 95% confidence interval. And the 95% confidence interval for this problem is this formula. So in our problem, we know this is 70.8. This is called the Tcritical. We'll get to that in just a second. This is 1.61 over the square root of 10. So all we would need to do now is find the Tcritical for the 95% confidence interval. Well, guys, that turns out to be really easy to do. If we think about the distribution of sample means, the middle 95% of our distribution of sample means is in the area of 2 Tcriticals. This one is clearly going to be negative. This one is clearly going to be positive. Well, how are we going to find those values? Well, we're going to find them using R. And if you think about it, guys, we've already found them, right? If we look back at what we found right here, when we were doing the line in the sand for the test of hypothesis and decision, we were ultimately finding the Tcritical for the 95% confidence interval because of the area to the left and the right of the negative 2.26. So guys, we kind of lucked out in this problem. Because we've already done this. Now this gets a little tougher when we get into when we get into other things, but right now it's really cool that it's staying this easy. So guys, if we go back to our confidence interval formula, we're going to get this. Guys, I'm going to put this in the calculator really quickly. And it looks like to me, after all the smoke clears, that we get a 95% confidence interval of 75.21 up to, no. I don't think I've had enough coffee to be doing a video this early in the morning. 66.39, actually 66.40, up to 75.20. And notice that the mu of equal to 74 is contained in our interval. I'll be throwing you a curveball on that one on your first assignment, having you look at a certain condition, come up with some values. But mean of 74 is in there, which corresponds to our decision of failing to reject. So let's go back to the very first of the problem and see what we've done here. National average on the test is 74. We want to see how our students at our school district compares. So we get a sample of 10 students. We examine their test scores. They get a mean of 70.8, 6.16. The dumbest thing you can do here, I call this stupid statistics, is to look at that 70.8 and say, well, that's lower than 74, so our students aren't measuring up. They are scoring below the national average. Guys, again, dumb statistics. Don't do that. Don't buy into that trap because it's not true. Granted, these 10 students have a mean that's less than 74. But if we were to take another sample of 10 other students, we'd get something different. Third group, something different. Fourth group, something different. If we keep taking sample after sample after sample, we're going to get different values. There's nothing holy about this 70.8 because if we got a sample of 10 different kids from our school, we get something different. It may be higher than 70.8, maybe 75. We don't know. There's going to be natural variation in our samples, so there's nothing special about the 70.8 other than it's just the sample that we have and the one we're going to work with. So we let the process play its way out and see if 70.8 is far enough away from the 74 for there to be a statistically significant difference. Sure, there's a difference. There always will be. 70.8 is not 74. 70.8 is below 74. The mean for these 10 students is below 74. That's not what we're trying to determine. We're trying to determine if the students in our school district, the difference is statistically significant from 74. And it actually turns out that it's not. By the way, our decisions on a test of hypothesis are reject or fail to reject. If we reject a null, we get statistical significance. If we fail to reject, we don't get statistical significance. So gang, at the end of the day, we failed to reject. Our test is not statistically significant, so there's no reason to think that our students are scoring different than the national average. In fact, we can go to our p-value. We can go to our confidence interval, and with a 0.95 level of probability, it appears that the average score for our students all of them is somewhere between 66.40 and 75.20. Now, let's see how this carries out in R. Okay? Turns out it's really, really, really easy. Kind of cool. There's a function in R that allows us to carry out a t-test. So if we just do t-test for our scores for a mu equals 74, my bad. Look what happens. Look familiar? This is our test statistic, degrees of freedom, and our p-value. I think ours was off a little bit, but you know, again, we used rounding. Yeah, it's off what, maybe 5/10 thousandths or something. So that's cool. So the alternative hypothesis is we tested not equal to, which is what we wanted, and you can see that our confidence interval is hopefully dead on for what we did. So yeah, it's pretty close. Okay, now if we want to do a one-tail test, and let me go back over to the blackboard and motivate this. What if we have reason to believe that our students aren't scoring as well, and we don't want to test generically a not equal to, just again a generic comparison of our student scores versus the national average, but we want a directional test, and we want to see if our students are scoring below the national average. So the intent of the test is different. When we had not equal to, we just want to see how our students compare with no emphasis on a direction. Now we have a little stronger test, at least a stronger intent for the test. We want to see if our students are actually scoring less than 74. Still going to test at alpha 0.05. Still using the same sample mean of 70.8. Same sample standard deviation of 6.161. And we still got 10 kids. Okay? Now, the person that knows squat nothing about statistics is going to say, oh, well, we're doomed. We have an average of 70.8, which anyone knows is below 74, so our students just aren't doing as well. No, absolutely not. This is, again, one sample of infinitely many. Samples vary. We have natural sampling variation in our scores. Let the process play its way out. The distribution of sample means is still going to look the same. It's going to be the t-distribution. Degrees of freedom 9. But this time we're going to put all of our rejection region in the left tail because we're testing less than. So our line in the sand now is going to be QT 0.05, 9. So our line in the sand now is negative 1.83. In terms of calculating our p-value, and remember guys, again, our t-value is negative 1.64. So even in a one-tail test, well, we turn out to have the same decision. This is not always going to be the case. Sometimes you'll get a two-tail test that'll lead you to fail to reject. You'll get a one-tail test that will lead you to reject. And you're going to have a tricky little problem on your first exam exploring that phenomena. Now, calculating the p-value, what would we do? Well, since we're doing a one-tail test, all we're worried about is the area to the left of negative 1.64. So guys, we got a handy dandy feature on R that takes care of that calculation for us. It's called PT. And we want the area to the left, so it works out really cool. So the area to the left is 0.0677. So gang, our p-value still greater than 0.05, but we fail to reject H sub O. Now notice that using the decision criterion at 0.05, we came closer to rejecting the null here than we did previously. But nevertheless, 0.067 is still greater than 0.05, so we still do not have statistical significance. Okay? Now, let me show you the way this is handled in R. So if we were to run a t-test, I crack myself up sometimes, 74, we would run it like this. And you can see that the test statistic doesn't change. Degrees of freedom clearly are not going to change. But our p-value, we don't multiply by 2 because we're putting all of our emphasis in one tail. Guys, the 95% confidence interval gets a little wacky here. This is, yeah, I don't like that. I think there's a way. I'm probably, let's see, I don't remember how to do this, but I think it's confidence interval. Scores. This is going to give me an error, I know. Alright, that's perfect. Yeah, I have to get back with you on that one. There's a way to calculate the confidence interval. Let's see. Well, I'll tell you what. Let me show you this. This is a kind of a cool feature to do a help for confidence interval. So it looks like we need our object, our parameters. Okay, a fitted model object, confidence level required. Okay, so a vector list of names. Okay, so let's try this. I don't know if it's going to work or not. Well, you're getting to see Darbo crash and burn. So level 0.95. All right, so let's see if this works. Actually, I don't think it is because I think we need that. Yeah. All right, what's going on here? I'll tell you what. Let me get back with you on that one. If we're running the one sample test, just remember that the 95% confidence interval that it gives you is not what you use. If you want the 95% confidence interval, even if you're running a directional test, you would also need to run a non-directional test, a two-tailed test, and use this confidence interval right here. So, guys, sorry for the confusion. I'm missing something, and I forget. I forget how to put that in, but hopefully that didn't just destroy the video. Okay. All right, gang, that's all I got. It's the next. Let me just give you a preview of what's coming up. I think I'm going to ultimately end up getting 5 videos up this week for my 5500 class and my 6600 class, who will also watch this video. I'm probably going to get 3 videos up for you guys. So guys, 5500 people, So far you have a video on the syllabus, and you have a video, kind of an intro to R, and you have this one, which is a t-test. The fourth one we're going to look at are going to be errors and power, and the fifth one we'll look at will be two sample problems. So fun, guys. Have a good one.